In this video, we'll discuss the problem and conceptual exercises of chapter 4 from the book James's Walker. So let's start. So this problem is based on a passage. Let me discuss what is given in the passage briefly. So it says that caterpillars eliminate their waste by ejecting pellets at high speed. Further, larger pellets are shot with lower speed, which can also be seen in this graph. Like if the mass of the pellet is 20 milligram, the speed with which it is launched is 1 meter per second. And if the mass becomes 5 milligram, then the speed increases to 2 meter per second. Question, it says that what is the maximum height above its launch site of a 20 milligram pellet that was launched at an angle of 20 degrees above horizontal. If the mass is 20 milligram, then it is launched at a speed of 1 meter per second. So we are given that V0 we have 1 meter per second and theta is 20 degrees above horizontal, and we have to find the maximum height. We have seen multiple questions like this. I'm just writing the formula. Y max is V0 sine theta whole square divided by 2g. We have all the values, we can plug it here. So y max, this will be equals to V0 we have 1, sine theta is 20 degrees divided by 2 multiplied with g is 9.81, and on solving we'll get this value to be 0.0060 meter, which can also be written as 6.0 mm. So the option D is correct, which is given in the question. So this question is also based on the passage that we discussed in the previous problem, and in this problem we have to find the maximum range of a 5 milligram pellet that lands at the same height from which it is ejected. So we have to find the range. Now when the mass of the pellet is 5 milligram, then its launching speed will be 2 meter per second. So V0 we have 2 meter per second, and we have discussed that the range is given by the formula V0 square over g multiplied with sine 2 theta. Now we have to find the maximum range, and for maximum range theta is 45 degrees. So put all the values here. V0 is 2 meter per second and its whole square divided by g is 9.81 meter per second squared times sine 2 theta. So it becomes sine 90 degrees, and sine 90 degrees is 1. So further solving we'll get this value to be 0.41 meter, which is equals to approximately 40 centimeter. Therefore, if you see the options, the option C is matching. So this is correct. Now in this question it is given that a golf ball is launched with the speed of 15 meter per second. So V0 we have 15 meter per second at an angle 57.5 degrees above the horizontal. So this theta we have 57.5 degrees. Now it lands at a height of 3.50 meter above the ground. So this height is 3.50 meter. Now there are two parts in this question that we need to solve. In the A part, we need to find the horizontal distance covered by the ball during its flight. Okay. So if you see the horizontal motion of the ball, we can use this equation: x equals to x0 plus v0 x times t plus 1 over 2 ax t square. Now there is no acceleration in the x direction. This is 0. This is our y direction. This is the x direction. So then we have x0 is also 0 because it starts from the origin. Now this is x equals to v0 x. We have v0 cosine theta, the horizontal component of the velocity, multiplied with t. Now from here time t is equals to x over v0 cosine theta. Now next let's see the vertical motion. So for that we can use this equation: y is equals to y0 plus v0 y times t plus 1 over 2 a y t square. Now from here this y0 is 0, so it becomes equals to v0 y. We have v0 sine theta multiplied with t. Acceleration we have minus g, so minus 1 over 2 g t square. Now let us put the value of t here. So it becomes y is equals to v0 sine theta, t is x over v0 cosine theta, minus 1 over 2 g t square. So t square we have x over v0 cosine theta, and its whole square. Now further, y is equals to this v0 and v0 will cancel it out, and we'll get x tangent theta minus this would become gx square over 2 v0 square cosine square theta, right? And we can take this y to the right side, so this would become 0 here, and here it is minus y. Now simplify this equation further. So this would become, I'm just taking the LCM, so x times tangent theta, and here this would become 2 times v0 square cosine square theta, then minus gx square minus y times 2 times v0 square cosine square theta, divide by 2 v0 square cosine square theta, which is equals to 0. When this term goes to the left side, it becomes 0. So finally we obtain this equation. Now after rearranging the terms, we'll get gx square minus x tangent theta 2 v0 square cosine square theta plus 2y v0 square cosine square theta is equals to 0. Now put the values. Now g we have 9.81, x square as it is, minus, now tangent theta is theta we are given to be 57.5 degrees, 2 I'm writing it here. v0 square is 15, so v0 is 15 square, then cosine square theta is 57.5, and then it all multiplied with x, then minus 2 times y. Now y is this vertical distance at point where it got struck, which is 3.50 meter. So this is 3.50 meter multiplied with v0 square is 15 square times cosine square theta. So cosine square 57.5, and it is equals to 0. Now after simplification, we'll get 9.81 x square, then here we'll get 203.9 x minus, sorry, this is plus 454.7 is equals to 0. Now this is a quadratic equation, so use your calculator to find the values for x from this equation. So x will be equals to 2.54 meter and 18.2 meter. Now this value corresponds to the horizontal distance when the ball was moving up, and this is when the ball is moving down. So our answer will be this value when it was moving down. Therefore, the horizontal distance covered by the ball is 8.2 meter. Let me represent on the figure also. So this horizontal distance covered by the ball is 18.2 meter. Now next, in the B part, we need to find the increase in initial speed that would be needed if the horizontal distance in part A increases by 7.50 meter. So if this value increases by 7.5 meter, then what would be the increase in the initial speed? So for that, use this equation. So I'm just copying it and then pasting it below. Now we'll simplify this equation for v0 square. So from here, v0 square will be equals to gx square divided by 2 times cosine square theta times x tangent theta minus y. We have obtained this by rearranging the terms. Okay. Now earlier we obtained the value of x to be 18.2 meter. Now this value increases by 7.5. So plus 7.5, which is equals to 25.7. Now let us find that what would be the initial velocity required when this x becomes 27.5 meter. So let's put all the values in this equation. So g is 9.81, x we have 25.7 and its whole square divided by 2 times theta remains same, so cosine square 57.5 multiplied with x times tangent theta. Sorry, x we have 25.7, tangent theta is 57.5 degrees, minus y also remains same, so 3.50 meter, and this is equals to v0 square. Now remove this square and put under root here, right? Now from here this v0 comes out to be as 17.5 meter per second. So if you see the increase in speed, that is delta v, Here this is 17.5 and earlier it was 15. You can see it here, this was 15. So 17.5 minus 15. So that is equals to 2.5 meter per second. So increase in speed should be 2.5 meter per second. So this will be the last question that we're going to discuss in this video. And with this question, the chapter 4, that is two-dimensional kinematics, is completely over. And then from the next video, we'll start with a new chapter, Newton's laws of motion. Okay, so let's discuss this final question. Now this question is similar to the example that we discussed in our previous videos, with a small change, and the change is that this time the dolphin is launched at an angle of 45 degrees above horizontal. Other thing remains as it is. So this is 45 degrees and this person drops the ball at a height of 4.10 meter and this horizontal distance is 5.50 meter. Also we are given that the initial speed, the launch speed for the dolphin is 12 meter per second. Now there are three parts in this question that we need to find. In the A part, we need to find the vertical distance between the dolphin and the ball when the dolphin reaches the horizontal position of the ball. Now to solve the A part, find the time taken by the dolphin to reach here. So horizontal distance traveled by the dolphin is 5.50 meter. So use the horizontal motion equation, which is x equals to v naught times cosine theta multiplied with t. Now from here this t is equals to x over v naught cosine theta. Now x is nothing but this d. Now put the values. So d is 5.50 meter, v naught is 12, cosine theta is 45 degrees. So time is 0.648 seconds. Now find the vertical positions of the dolphin and the ball at this time. So first we'll find the vertical position for the dolphin. So for the dolphin, use this equation. We can write yd is equals to v naught sine theta multiplied with t minus 1 over 2 gt square. Now put the values. V naught we have 12, sine theta we have 45 degrees, and time we have to take it to be 0.648 seconds, minus 1 over 2, g is 9.81, time is 0.648 seconds and its whole square. Now from here the yd, it comes out to be as 3.44 meter. So the dolphin height is at this position we have 3.44 meter. Now find the height of the ball corresponding to this time. So when the person drops the ball, initial velocity for the ball in the vertical direction will be 0 and then it will goes on increasing due to the gravity. So we can use this equation for the ball. Yb is equals to y naught plus v naught sine theta multiplied with t minus 1 over 2 gt square. And since there was no initial velocity, so this is 0, and y naught, initial height for the ball is 4.10 meter. So this is 4.10 minus 1 over 2, g is 9.81, t we have to take it to be 0.648 and its whole square. So on solving we'll get this value to be equals to 2.04 meter. So by the time the dolphin reaches at this height, the ball have reached here, and this height we have calculated to be 2.04 meter. So the ball misses and this vertical distance is our miss distance, that what is given in the equation that we have to find. So delta y, the distance with which the dolphin missed the ball, is this is 3.44 minus 2.04. So that comes out to be as 1.40 meter. So the dolphin missed the ball by this much of distance. So this is the answer for the A part. Now next in the B part, the question is saying if the dolphin's launch speed is reduced, will the miss distance increase, decrease or stays the same? The answer is it will remain the same. The miss distance will not going to change. Even though the speed is reduced, the launch angle is kept at 45 degrees. And if the speed is reduced, the dolphin will take longer time to cover this horizontal distance, no doubt. But both the dolphin and the ball will have fallen away from the zero gravity position by the same amount during that time. That is, the missed distance will not going to change. Now let us prove this by solving the C part. In the C part, we have to find the missed distance for a launch speed of 10 meter per second. So launch speed is decreased. So now let us check the missed distance. So we're going to follow the same procedure to find the missed distance. Just to change, V0 becomes 10 meter per second. So first find the time. So for this time, we can use this equation, d over V0 sine theta. D is same, that is 5.50 meter. D is 10 cosine 45 degrees, and that comes out to be as 0.778 seconds. Now find the vertical position for the dolphin corresponding to this time. So YD is equals to, we are using this equation now. So V0 sine theta. So V0 we have 10, sine theta is remaining the same, 45 degrees. Time, this becomes 0.778 seconds, minus 1 over 2, G is 9.81, T square is 0.778 and its whole square. Now on further solving, we'll get the value of YD to be equals to 2.53 meter. Now find the position for the ball corresponding to this time, YB. So YB would be Y0 minus 1 over 2 GT square. Y0 is 4.10, same as of the above. 1 over 2, G is 9.81, T is 0.778 and its whole square. Now from here, YB comes out to be as 1.13 meter. And the missed distance, YD minus YB, this will be equals to, this is 2.53 minus 1.13. which is equals to 1.40, which is same as that of this value. Therefore, the missed distance will not going to change even though the speed is reduced.